So let's take a look at this terminology, linear versus nonlinear. The idea of linearity is it's probably going to seem a little confusing at first in terms of what equations we call linear versus what do we call nonlinear, but it's ultimately the same linear that we were talking about in Math 22A with the idea of linear combinations. For example, if you've got a collection of vectors, let's say we just call these vectors v1, v2, and v3. If we're talking about a linear combination of these vectors, what would it mean to make a linear combination? What could you do to these vectors that counts as linear?
You can make like a linear combination out of them, like AV1 plus BV2 plus CV3.
Yeah, we could have like a scalar multiplier, A times this one, B times this one, C times this one, and then all added together. So this would be a linear combination. We'd say that a linear combination of V1, V2, V3 is essentially any result you can get by multiplying each one of those vectors by a scalar, maybe just a real number, and adding up those results. So that would be a linear combination, maybe a new vector we might call W. So in that case, we'd say W is a linear combination of V1, V2, and V3. For differential equations, we use a very similar meaning of the word, but instead of talking about vectors, we're talking about some unknown function, let's say y and its derivatives. So let's say you have a function, and presumably we're also talking about its first derivative, maybe its second derivative, maybe its third derivative, and so on, up to whatever order you're talking about. So for instance, if we go up to the third derivative, this would be a third order differential equation. So much in the same way that a linear combination of vectors is just each of those vectors multiplied by a scalar and added together, we're going to say we can do the same thing to these. We can multiply each one of these functions, y and its derivatives, by something. Let's say, we usually call this a sub 0. If you think of the function itself as the 0th derivative, and then a sub 1, a sub 2, a sub 3, and then add those together. The difference is the A's don't have to be constants. In fact, these coefficients don't have to be constants either. These A functions, A0, A1, et cetera, can be functions of t. They just can't have any y in them. They can be functions of t or x, whatever the independent variable is. And then those all add up to presumably some other function, let's say b of t. So in general, if you could write a differential equation in this format, something y plus something y prime plus something y double prime and so on equals something, and all those somethings are either constants or functions of the independent variable, but not functions of y or its derivatives, then that counts as a linear differential equation. Any questions on the meaning of that so far?
No, that makes sense. Thank you.
Yeah. And of course, it doesn't have to be third order. You can have any order you want. You could have, like, for instance, just something y plus something y prime equals something. So that would be a first order linear equation. We're going to be dealing with second order equations in great detail later on in chapter 3. And as you might expect, linear equations are usually much easier to solve than nonlinear equations. There's a whole field of study that's just how to solve linear equations. And then much of solving nonlinear equations involves either maybe it's something we know how to solve, or if it isn't, finding a way to approximate it with a linear differential equation, solving that linear differential equation to get an approximate solution. As a counterexample, what would be something you could do that would make a differential equation nonlinear? How would you write an example of a nonlinear differential equation?
I think you could try to multiply y to any of
Yeah, because the important thing is each of these derivatives is multiplied only by functions of t or x or whatever the independent variable is. If you multiplied one of them by y itself or by another derivative, for instance, let's say you had y prime times y equals 5. This would be a nonlinear differential equation because y prime is multiplied by y, not by just a function of t. That is, not by a known function of t. Or if you had, let's say, a y squared. The y squared here makes that a nonlinear differential equation, regardless of anything else. If you've got a y squared here, that can't be written as just something times y. So this makes it nonlinear. But as long as it's just something y plus something y prime plus et cetera, or can be written in that format, then it counts as linear, even if the multipliers are some complicated nonlinear functions. Like if you had, let's say, tangent of t squared times y minus 1 over t cubed times y prime plus logarithm of t times y equals the 5th root of t. This still counts, oh, let me make that a double prime. This still counts as a linear differential equation because it's still just some function of t times y plus some function of t times y prime plus some function of t times y double prime equals some function of t. It's still just a linear combination of y and its derivatives. So this counts as linear. Any questions on that distinction so far? And one other bit of terminology that's going to become much more important later on. This b of t here, the thing, and we usually think of this as the thing on the other side of the equation, but of course it doesn't have to be written in this exact format. You could write it as like something maybe a0 times y plus b equals a1 times y prime. So b isn't necessarily the thing on the other side of the equation. The important thing is it's the one term or the terms grouped together that don't have y in it. So for instance, if we had something like 3y plus cosine of 2t equals 5t y prime, this cosine of 2t is still the b of t part because it's the part that doesn't have y in it. And that part is usually called the non-homogeneity. And its existence, the fact that it has this term without a y in it, makes this differential equation non-homogeneous. That is, a linear differential equation that has this term without a y in it is a non-homogeneous differential equation, or sometimes called inhomogeneous. The part that makes it non-homogeneous, the part without a y in it, is the non-homogeneity, also sometimes called the forcing function. Largely because in applications, especially applications involving physics, this extra function often represents an external force added to the system, like something pushing on an object from outside, or in circuits, it often represents an extra voltage applied by a battery or a generator. But in general, it often represents some extra push from outside the system. And if that's not there, if you have equals 0, then we'd say the differential equation is homogeneous. So if it was something like a0y plus a1y prime plus a2y double prime plus a3y triple prime equals 0. And of course, again, it doesn't have to be 0 on one side of the equation. It just has to not have a non-homogeneity. It has to not have any term without y in it. We would say this is a homogeneous differential equation. And as you might expect, the homogeneous differential equation tends to be much easier to solve than the non-homogeneous differential equation. So when we get to chapter 3, the first half of it is going to be largely about solving homogeneous differential equations of second order. And then the other half of the chapter is going to be what happens if it's non-homogeneous. Any other questions on the terminology there so far?
Just to clarify, so if it's just equal to any other constant that doesn't depend on t, that's homogeneous, right?
If there's any term that doesn't have y in it, it would count as non-homogeneous.
Oh.
So for example, if you had, let's say, 3y prime minus 5 plus 2y double prime plus cosine of t y equals 0. This would actually be non-homogeneous because it has this term without y in it. And it would probably be easier to rearrange this in a sort of a standardized format to put the term without y in it on the other side. So you'd have something like 2y double prime plus 3y prime plus cosine t y equals 5. That meant just writing it in that format makes it more obvious that it's non-homogeneous. But even if it's written like this with an equals 0, this is still a non-homogeneous differential equation because it has this term without y in it.
Oh, thank you. Yeah.
But writing it in this standardized format with the term without y on the other side makes it easier to see that. So it's a good idea to write it in that format when you can. Also, one other important thing about a homogeneous differential equation, if you've got y or its derivative in every term equals 0, what value of y will always be a solution to this homogeneous differential equation?
0.
Yeah. If your differential equation is homogeneous, then y equals 0 is always going to be a solution. Because if y is 0, then all its derivatives will be 0. And so all these terms add up to 0. So if you have a linear differential equation that's homogeneous, then 0 will always be a solution. And that goes in the other direction too. If 0 is a solution, then you know it's homogeneous, as long as it's linear anyway. Whereas for a non-homogeneous differential equation, if you plug in 0 for y, all these terms resolve to 0 and not equal to b of t. So that means 0 is not a solution of a non-homogeneous differential equation. Any other questions on the terminology there before we move on? And again, we're going to revisit a lot of this stuff in chapter 3 as well, especially for second order differential equations in specific. But let's take a look at that idea of container problems as one application of first order differential equations. Container problems are a fairly large category. It's based on the foundational idea. The reason we call it a container problem is the classic example is you've got some container of, let's say, water. Water with a contaminant in it. So you've got water, but there's something else mixed in with it, maybe salt, for instance. So you've got particles of salt dissolved in the water, and maybe you're trying to mix in more salt, or maybe you're trying to flush the salt out by pouring pure water into it. But either way, you've got some input of fluid pouring into the tank. And also you've got an output. You've got water draining out of the bottom of the tank. Water draining out the bottom of the tank. And the input and the output both influence how much of the contaminant is in the tank. For now, let's assume that the water is flowing in and flowing out at the same rate. So the total amount of water does not change. Let's say the input is, let's say 10 gallons of water per hour. And the output is also 10 gallons of water per hour. So we're not changing the amount of fluid in the tank. And let's say we know that amount of fluid. Let's say the amount of fluid the tank holds is, let's say 1,000 gallons. (1,000 gallons of salty water). And let's say we also know the concentrations. Let's say we start with 5 grams of salt per gallon. 5 grams of salt per gallon of water. And let's say we also know that the water that's flowing in has a certain amount of saltiness to it. Let's say the input is even more salty. Let's say the input has 8 grams of salt per gallon of water. And I think that's all the information we're going to need. We know how salty the water is to start with. We know how much water the tank holds. We know the water flowing in is a little bit saltier. And we've also got the rate at which water is flowing out. And let's say what we care about here is how much salt is in the tank at any time. And let's just declare a variable for that. Let's say capital S of T equals the amount of salt, grams of salt in the tank. After T hours. So we want to figure out, for instance, how much salt is in the tank 5 hours later or 10 hours later or whatever. Any questions on the general situation so far? And since the amount of salt is changing as time passes, that makes it very well suited for modeling with a differential equation, because differential equations are all about rates of change. How fast is this thing changing as time passes? Or how fast is this thing changing as some other thing changes? So to make a differential equation that models this, we can start with the idea of rate of change, ds dt. And units are good to keep in mind here. Anytime you're dealing with a physical situation, it's good to think of it in terms of units of measurement. S is going to be measured in what unit of measurement, what quantity?
Grams.
Yeah, S is measured in grams, and T would be measured in
Hours.
Presumably hours. So that means this is going to be measured in grams per hour, specifically grams of salt per hour, if that matters. So keep the units in mind here. This is grams per hour. So that means that's what we want all of the other terms to be measured in also. The other side of the equation must also be measured in grams per hour. And what things are influencing how much salt is in the tank or how fast that changes? What's causing the amount of salt to change?
The in function, the input.
Yeah, we've got this inflow. And also, what else do we have?
The output.
Yeah, we've got output here. So we've got to keep both of those in mind. We're putting salt into the tank by pouring salty water in the top. But also, as fluid drains out the bottom, that fluid is taking some salt with it. Because the water in the tank right now has some salt in it, some of that salt drains out the bottom, assuming it's evenly mixed together. And that's something you'll often see in problems about this. You'll often see word problems that say the well-stirred mixture drains out the bottom. That just means that we're assuming that all the salt is evenly distributed throughout the tank, that it's not like clustered in one corner or something. So all we really need to care about is how fast is salt entering the tank and how fast is salt leaving the tank. And we often abbreviate this as rate in minus rate out. That is, anything involving salt entering the tank, specifically how fast is it entering per second or per hour, because we want grams per hour, minus any effects causing salt to leave the tank, also measured in grams per hour. And this is not just for salt dissolved in water. You can use a similar approach for any situation that can be thought of as a container that holds a finite amount of stuff, with stuff entering and stuff leaving. Salt in a tank of water is the classic example, But what are some other situations where you want to keep track of how much of something there is in some enclosed region in terms of how much is entering and how much is leaving? What would be another example where you've got some quantity that's changing because some stuff is causing it to increase and other stuff is causing it to decrease in terms of real world examples?
Maybe like airflow.
Airflow could work if you have like a chamber or maybe a room or a cavern or something, and you've got air flowing in one side and air flowing out the other side, or maybe several locations where air can flow in, several where air can flow out. Maybe you want to keep track of how much air is in the room right now in terms of maybe number of moles of nitrogen or moles of oxygen. Maybe the rate in is dependent on pressure outside and pressure inside, and the rate out is dependent on pressure inside and pressure somewhere else, as well as, of course, resistance of the input and output holes.
Maybe also like temperature or like temperature change.
Yeah, temperature works well. If the container is some object, maybe you've got like a block of iron, or maybe you've got a building in the interior of the building, and the stuff in the building would be thermal energy. And you could look at this in terms of heat flow. So this would be rate of change in the thermal energy of the building. This would be the rate at which heat flows into the building from outside, maybe also influenced by heaters or people in the building shedding body heat. And then rate out would be how fast does heat leave the building and how fast are air conditioners pumping heat out of the building. So as long as you take both of those into account, anything causing heat to enter the building minus anything causing heat to leave the building, you can set up a differential equation for heat flow and modeling the temperature of the building. Another common example is population. Even though population isn't classically thought of as stuff in a container, if you think of the container as, let's say, a city or a forest or a nation, some geographical region where a population can exist, and if S represents the number of individuals in that population, ds dt would be how fast the population is changing. For instance, what would be rate in that case? What factors cause a population to increase?
Reproduction.
Yeah, reproduction, birth rate. So rate in would include birth rate. And also maybe instead of birth rate, you could have individuals coming in from somewhere else. So rate in could include birth rate plus immigration rate. And then rate out, what would cause the population to decrease?
Disease or like predators.
Yeah, anything causing death of the population. So rate out would be death rate. And also maybe some individuals just leave the region. So this could be death rate and emigration rate combined. But even though population is not classically thought of as literally a container, you can still model it using the same techniques. In this case, the container would be the geographical region where the individuals live. Rate in would be birth rate and immigration rate combined. Rate out would be death rate and emigration rate combined. So as long as you can find some ways to set those up as formulas, maybe constants, maybe depending on time, maybe even depending on population itself. For instance, birth rate is usually proportional to the population right now. So as long as you can write those as mathematical expressions, you have a differential equation. And if you can solve that, you'll have a formula for population at any time in the future, at least as a good approximation. Any other questions on the setup so far? So let's try actually writing out rate in and rate out for this situation right here. Ideally, we want these to be measured in grams of salt per hour, but we have an inflow rate measured in gallons of water per hour. So how can we change gallons of water per hour into grams of salt per
hour? We could do some dimensional analysis.
Yeah, because gallons of water per hour, that's gallons over hours. So if we write that out, we've got specifically 10 gallons per hour. And I'm going to fill in gallons of water per hour. What would we have to multiply that by to get grams of salt per hour instead? We want
We
to
can
keep hours, right?
Yeah, we could multiply gram of salt per gallon of water.
Yeah, because we want to introduce grams of salt but cancel out gallons of water. So we're going to need to multiply by grams of salt over gallons of water. And we actually have that measurement. We know grams of salt per gallon of water of the fluid flowing in. That's specifically going to be 8 grams of salt per gallon of water. So that'll give us the correct units because grams of water, gallons of water and gallons of water in the numerator and denominator cancel out. So we're left with just grams of salt per hour. In this case, specifically 80 grams of salt per hour. That would be the rate. Any questions on that so far? So generally what we're doing here is we're multiplying the current in the sense of flow rate of the fluid multiplied by the concentration. Fluid flow current in gallons of water per hour times concentration, grams of salt per gallon of water, gets the gallons of water to cancel out, so you're left with grams of salt per hour. Any questions on the units of measurement there so far? So that gives us our rate. Looks like rate N, 8 times 10 would be 80 grams of salt per hour. As for rate out, we can still use the same idea of current times concentration. Gallons of water per hour of flow rate times grams of salt per gallon of water of concentration. For the rate out, what's the flow rate for the output?
Um, 10.
Yeah, still 10. We can still use 10 gallons of water per hour for the current. For the concentration though, what can we use for concentration for the output?
Like S or S over?
Yeah, we're gonna have to use something about S. We can't just use the 5 grams of salt per gallon of water because that's only the amount it has to start with. As soon as the fluid starts flowing, that's gonna change.
Isn't it like 5S over 1000?
Yeah, I think that should work because 5, wait, where's the 5 coming here?
The 5 grams of salt.
There's initially 5 grams of salt, but remember that's only at the very beginning. As soon as fluid flows, that's going to change. So the 5 gallons of salt per gallon of 5 grams of salt per gallon of water, this doesn't really play into the differential equation itself. But how would you describe this information, the information about what it starts as?
At t equals 0 or at t0, 5 grams of salt.
Exactly. This is what happens at time 0. This is the initial conditions. So we essentially have an initial value problem here. All this stuff is the differential equation itself, or can be turned into a differential equation. This part describing what's going on at the beginning, that's the initial condition. So we can ignore that while we're setting up the differential equation itself. We can come back to it when we have the general solution and need initial values. But for the rate out, we've got 10 gallons of water flowing out per hour. We want to write the concentration here. And remember, concentration is grams of salt per gallon of water. So if you consider the whole tank, how many gallons of water do we have?
1000.
Yeah, and that's going to stay 1000 because we have every hour 10 gallons flow in, 10 gallons flow out. So the 1000 gallons total doesn't change. If it did change, like if the inflow and outflow were not the same current, then this wouldn't be a constant. This would end up being a function of time, and that gets more complicated. But for now, that's just a constant. As for grams of salt, we don't know how much salt is in the tank at any time, but what are we using to name that? What's the name we've already assigned to salt in the tank right now?
S of t.
Yeah, that's just S of t, the function. So there's S grams of salt at any time divided by 1000 gallons of water. That's the concentration, salt per gallon. multiply that concentration by the flow rate, 10 gallons of water per hour. Gallons of water and gallons of water cancel out. We're left with grams of salt per hour. And that'll specifically be 10S over 1,000. So that's our rate out, 10S over 1,000. And I guess that's going to formally be in per hour. Because S has grams already sort of baked into it. So this ends up being grams per hour. It's just that grams is inside the S right now. Any questions on that setup so far? So let's simplify a bit, see what we get. Looks like we've got ds dt equals, and since everything's now in grams per hour, I'm going to leave off the units and just treat this as a numerical problem. 80 minus 10 over 1,000 simplifies to 1 over 100, so 1 over 100s. That is our differential equation that we use to model this whole situation. And of course, we also want to list out the initial value problems, specifically S of 0 equals, there's 5 gallons of salt per gallon, or 5 grams of salt per gallon of water to start with. How does that translate into an actual amount of salt?
So initially there's 5,000 grams of salt in the whole container.
Yeah, because it's 5 grams per gallon. We've got 1,000 gallons. So multiply by 1,000 gallons, we get 5,000 grams of salt. So this is now the initial value problem. We've got a differential equation, we've got an initial value, and we can solve this to find out S as a function of t. Any other questions on the setup so far? Also, before we even solve this, we can analyze the end behavior. We can figure out what's going to happen after a long period of time, looking at the limit as t approaches infinity before we even solve it. Because after a long time, presumably this is going to go through a process of rapid change, because we're putting in salt at a higher concentration than it is already. So presumably that's going to make it increase. But gradually the salt in the container is going to match the salt flowing in. So it's going to level off to some asymptote. How could we figure out what that asymptote is, the final amount of salt in the container?
It will be 8,000 because I guess like, because like the in function will just like overpower the out function. So it'll just be like 8,000.
Yeah. Yeah, we can assume that the amount of salt is going to increase as long as the input concentration is greater than the output concentration. Eventually, the output concentration will match the input concentration when the concentration inside is the same as the concentration flowing in, which would be 8 grams per gallon. 8 grams per gallon for a 1,000 gallon tank should be 8,000 gallons or 8,000 grams. So conceptually, we should expect 8,000 grams because that's when the concentrations match. We could also find that using the differential equation itself, because after a long time, what should we expect the derivative to settle down to? If this is approaching some asymptote, what's the slope going to be after a long period of time?
0.
Yeah, after a long time, we should expect the slope to be 0. So to find that equilibrium, you can set the derivative equal to 0 and figure out what S has to be. So if we set the derivative equal to 0 and solve for S, what do you get?
$8,000.
Yeah. Add this to both sides, multiply by 100, S equals 8,000. So mathematically, we also find that 8,000 is the equilibrium solution we should expect. So the graph of this, if we were to set up, for instance, a direction field, time versus S, and we've got 8K, 8,000 there, we know that at 8,000, when S is 8,000, the slope is 0. So that's going to be an equilibrium there. Anything below that, conceptually, what would you expect to happen to the salt in the tank if it's not salty enough yet, if there's less than equilibrium salt?
Be a positive slope.
Yeah, we'd have a positive slope. Presumably a pretty weak slope if we're close to equilibrium, and then a steeper slope further down. So something like that. Or if the tank starts off too salty, let's say this started off at, let's say, 15 grams of salt per gallon of water, what would you expect to happen?
It would just decrease to match the in.
Yeah. It's going to decrease towards equilibrium. We can also see that from the differential equation itself. If S is too large, then this term being subtracted overpowers the 80 being added. So the result is a negative slope. If we're just a little bit above 1,000, it'll be just a little bit negative slope, then steeper and steeper. So that would be what our direction field would look like. And the solution curves themselves look an awful lot like what kind of functions? What kind of function does that look like? If it's, let's say, starts off steep, then levels off towards equilibrium.
It's like a log function.
Log function would be growing forever, though. A logarithm function does not have a horizontal asymptote. But what function does start off steep and then get flatter and flatter and flatter? What's the opposite of a logarithmic function?
Oh, 1 over.
Well, that 1 over something would also have a vertical asymptote, but this is not like coming down from infinitely salty. What's a function that starts off at some finite value and then decays towards some other finite value? What kind of decay is this?
Exponential?
Yeah, this is looking a lot like exponential decay in terms of the behavior of the graph. So I would expect this to be some sort of exponential function as the solution. In fact, we could find the solution as well. I mean, we can get an idea that everything's going to be approaching 8,000. If it starts off with less than 8,000 grams of salt, it's going to increase quickly, then level off towards 8,000. If it starts off with more salt than 8,000 grams, it's going to be flushing salt out and leveling off towards 8,000 from above. By the way, what would we call that kind of equilibrium here? If everything's approaching equilibrium from both sides, what do we call that? Has that terminology shown up in class yet?
I don't think so.
In general, if you have, because equilibrium just means if you start there, you'll stay there forever. Like if we had started with 8,000 grams of salt in the tank, it would just stay at 8,000. But if you, so we call that equilibrium. But if you start a little bit above equilibrium, you get pushed back down to equilibrium. If you start a little below equilibrium, you get pushed back to equilibrium. So that is called a stable equilibrium. Stable in the sense that it's difficult to change. If you try to go away from it, you just get pushed back towards it. Whereas unstable equilibrium would be if you had a slope field that looked more like this. So if you stay at equilibrium, or if you start at equilibrium, you stay there forever. But let's say you start a little above equilibrium, you get pushed further away from it. Or if you start a little below equilibrium, you get pushed further away from it as well. So this would be an example of unstable equilibrium, whereas the one we're actually looking at with the tank problem here is stable equilibrium. There's also what's called semi-stable or half-stable equilibrium, which is when it looks stable from one side but unstable from the other. Like one side pushes you back towards equilibrium, the other side pushes you off to infinity. So that would be called semi-stable or half-stable. Any other questions on those so far?
Yes, so is it reasonable to expect to have an equilibrium solution for container problems?
Generally, yeah. I mean, for a container problem where you're just pouring in water with some constant concentration, the tank of water is eventually going to approach the same concentration as what's being poured into it. So I would generally expect a tank problem like this to have an equilibrium solution. Exceptions might be if the concentration changes as time passes. Like maybe you're pouring in water that's not a constant amount of saltiness. Maybe you're pulling it in from maybe a river at a tidal estuary where at high tide it's salty and at low tide it's less salty. So maybe instead of a constant 8 grams of salt per gallon, maybe you've got some amount of salt that changes sinusoidally as time passes. Or maybe you're pouring in water at 10 gallons per hour and pulling out water at, let's say, 12 gallons per hour. So the amount of water in the tank is gradually diminishing And maybe you're trying to find what's the concentration of salt in the last drop that leaves the system. In a case like that, the main difference would be that you don't have a constant 1,000 gallons. You'd have an amount of salt or amount of water that changes as time passes. So you need to first set up an equation for how much water is in the tank at time t, and use that in your setup as well. So there's a lot of variability in a situation like this, a lot of different ways to make it a little more complicated in some way. Any other questions on that so far? And one last thing to do here. Now that we've actually set up this differential equation and used the idea of a direction field to analyze the end behavior, so we know after a long time it should approach 8,000 gallons of salt. What if we want more detail? How do we actually solve this differential equation for S? First of all, does it count as linear?
Yeah.
Yeah, this is definitely linear. We've got something S prime plus something, like you can move this to the other side, 1 S prime plus 1/100th times S equals 80. So that is definitely linear. And what technique can you always use to solve any first order linear differential equation?
You just integrate both sides?
You can't quite integrate both sides yet because one side has an S prime that is derivative with respect to t. If you try integrating both sides with respect to t, you'd have to integrate S with respect to t, and S is a function of t that we don't know yet. So you can't just integrate both sides yet. But in general, if it's linear, have you seen the technique integrating factors yet? The integrating factors method?
Yeah.
Anytime you have a differential equation that's linear and first order, you can always use the integrating factors technique. So if you wrote this, for instance, as, let's say we move everything to one, we'll move all the S terms to one side. S prime plus 1/100th S equals 80. This could be analyzed using integrating factors. For instance, you can multiply both sides by mu. Figure out what mu has to be by assuming that mu times 1/100th equals mu prime. And then replace this with the product rule, mu times S prime. However, that's not necessarily the easiest method to use here. What I would do instead in a case like this, it's important to note, I think, that this entire side of the equation doesn't have any t in it. It's just a function of S. So how else could you solve this? You can't just integrate both sides yet, but what could you do first that would allow you to integrate both sides?
Can't you multiply dt on both sides?
Yeah, we could multiply both sides by dt. And of course, we can't integrate this with respect to t because we don't know what S is, but how could we get rid of this entire piece?
Divide.
Yeah, divide that out. 1 over that whole thing.
Oh, also, this is a quick question with regards to the integrating factor.
Mm-hmm.
Like when I went to like the office hours, they were saying, oh, you find the integrating factor, multiply the whole ODE by the integrating factor, but the professor's like, you could just use the formula. Which way do you think is better?
I usually find that if I try to memorize a formula, I end up forgetting it at some point.
All right.
So I would usually, I mean, it's good to know the formula just as a shortcut to save time, but also make sure you know where that formula comes from. The idea that you're assuming that mu prime equals that function times mu, or that multiplier times mu. And then you're just solving a separable, simpler differential equation from mu. It works out to just e to the integral of t dt. So make sure you know where that comes from.
All right, thank you.
As for this one, you could solve it using integrating factors because it is linear, but it also happens to be separable. And I think separation of variables is usually a much faster and easier approach. So multiply by dt, divide by this whole function of S. Now this entire left side of the equation is just S and no t. The entire right side is just t and no S. So at this point, you can integrate both sides. This one's going to require some u substitution, but not too bad. This side is just going to be t plus c. then isolate S to get an implicit or explicit solution, S equals something about T. At that point, you can plug in the initial conditions, T equals 0, S equals 5,000, to find the value of C and get a specific solution. But separation of variables, I think, is going to be the best method in a case like this. Any other questions on that? All right, then I will see you next time.